Good afternoon, most respected Dr.Reji Philip, Dr. Tia Shirley, the head of the department, or other faculty members from our college and other colleges, my dear students and students from other institutions who have joined. A warm welcome to you all for the last webinar session of this series, which we have been conducting since November 7. So this is the 6th session of the series, and we are very honored to have such an eminent speaker like Reji. Maybe to all of us, through the words of Dr. Sham, all have heard about you a lot. We are so grateful and thankful that you have joined. Let me introduce Dr. Philip. He has and PhD, as a postdoc experience from TIFR Mumbai and Regensburg University, Germany. His research interests includes laser-produced plasma, ultra-fast spectroscopy and nanostructuring using laser pulse. Presently, he has 2 patents and about 180 research publications in his credit. Once again, I welcome Reji Philip, Professor Reji Philip, to this event and request him to address this once again.
Thank you very much. Am I audible to all of you? Okay, very good. So I hope you can see me also.
Yes, sir.
Yes. Okay. First of all, thanks a lot, Dr. Srikanth, for inviting me to give a talk in the seminar series. So I will be speaking about some fundamentals and applications of nonlinear optics. I am Reji Philip. I am from the Dharma Research Institute in Bangalore. So when we speak about nonlinear optics, we cannot miss the name of Professor Nicolaas Bloembergen. He is considered as the father of nonlinear optics. He was born in Netherlands, then Holland, in 1920, and he passed away just 3 years before in Tucson, in Arizona. So he's a Dutch-American physicist, and he enrolled in 1938 at the University of Utrecht to study physics. And he left Netherlands in 1945 to Harvard University because, as we know, that's the time of Second World War. And he ended up with Edward Purcell in Harvard, who had just discovered NMR, nuclear magnetic resonance. So as we know, NMR is very useful nowadays in hospitals for taking MRI images, magnetic resonance imaging. So a lot of the internal body organs, etc., can be very clearly clean. Better, you can seen better compared to a CT scan when we use MRIs. So the fundamental principle of that is nuclear magnetic resonance. Then he was part of the team that developed the first NMR machine, and he enjoyed classes from very celebrated scientists like Schwinger. And his thesis was submitted to the University of Leiden, and he got his PhD degree in 1948. Then he went to Holland but came back and became an associate prof in Harvard in 1951. 1958 he became a citizen, and in 1981 he received the Nobel Prize in Physics with Shallow and Seekman for the work in laser spectroscopy. So when I originally wrote this page, he was working at the University of Arizona faculty a few years before, but he is no more. He passed away in 2017. And I had the good opportunity to meet Professor Bloombergen in 2012 in the US. And he actually told me that he had visited the Raman Research Institute in 1977. So he had a good memory. And I was very happy to hear that. So now coming to our topic of discussion today. When we speak about NLO, we have to start from electromagnetic waves. So as we all know, this is how we represent the electromagnetic wave in a pictorial way. And these waves are governed by the Maxwell's equations. And this is the spectrum of electromagnetic radiation. At the lowest energy end, we have radio waves, which we use for radar, TV, FM, AM, and now also for mobile communication. And that's the longest wavelength. And as we reduce the wavelength, the energy increases, because as we know, the energy of a photon is h nu. Of course, that's a photon picture. But as you reduce the wavelength or as you increase the frequency, the energy increases. And from radio waves, we come to infrared, then visible spectral region there. So you can see it's a very, very narrow band. That's where the entire violet to red, the VIBGYOR, lies. Then we have ultraviolet, then X-rays, and then gamma rays. So that's the constitution of electromagnetic radiation. Now, the interaction of light with matter is basically the interaction of electromagnetic radiation with electrons. So we have to think about the electrons which are there, the bound electrons in any atomic or molecular system. In this particular example, we are talking about metal nanoparticles. So this is a good example. That's why I selected this. So when we have some metal nanoparticles and we are putting the electric field is going in the positive direction, and in the next half cycle it's going in the negative direction. So what happens here is, in the positive direction, the electron cloud gets attracted to the positive part of the field all the time. Because the field is alternating in direction like this, the electrons also will oscillate accordingly. This is a collective oscillation of the electrons for a nanoparticle system. And when you have a collective oscillation like that, we know that it's called a plasmon. So this is especially for plasmonic oscillation, but the case is true for electrons which oscillate even in a non-collective fashion. Only in metal nanoparticles you see collective oscillation of this kind. If you take normal materials, then it's not collective. Electrons are individually oscillating, and that oscillation is the response of bound electrons to an applied electromagnetic field. So this results in linear as well as nonlinear phenomena. And the linear phenomena, as we know, are characterized by the refractive index and the absorption coefficient. And in nonlinearity also we have same thing, but modified refractive index and modified absorption coefficient. And the nonlinear part is also divided into two. One is called the perturbative nonlinear optics. That's what we will discuss today. And we will not go into the strong field NLO, which is where we use extremely powerful laser beams to irradiate materials. And that kind of power will lead to ionization of the material and forms a plasma and all. So we will not talk about that today. So basically there are three regimes like that for light matter interaction. So the linear regime is where the response of the medium to the applied electric field in the EM radiation is linear. So if this is the polarization, electric polarization induced in the material because of the applied field E, and if this is the kind of relationship, so we can see it's linear. P is proportional to E. It is not proportional to E square or anything. So this is a linear response, and this is the domain of linear optics. But in the perturbative nonlinear regime, we will have to add extra terms into this expression. So we will have an E square term, an E cube term, like that. And when we go beyond this, we have the intense field regime, the intense field nonlinear optics regime, which is based on ionization. So what happens here is medium gets ionized via multiphoton tunnel and over the barrier ionization phenomena, and then plasma is formed, and the free charges accelerate under the field, causing further collisional ionization. The plasma will absorb light, it will emit light also. But we are not going into plasmas. We rather look at the day-to-day applications of nonlinear optics. So which are these? There are three areas. Three areas can be broadly classified. So the first one is the diversification of lasers and light, where you generate new colors, that is new frequencies. Secondly, you can control the spatial and frequency nature of the laser beams. Then you can generate pulsing lasers, like pulse lasers. We can make nanosecond laser pulses. We can make femtosecond, picosecond, like that. We will see all those things now. And then there is laser matter interaction. So there we have machining, micro machining using laser beams. In fact, some medical applications also come here. Then there is spectroscopy, analysis, all that happens in material interaction. Then there is information technology where NLO has an impact. So there is telecom, signal processing, data storage, sensors. So we will see some of these in today's talk. So the first one is the generation of new frequencies. So how does this happen? To understand this, we will look at the electrical susceptibility of a material. So this, we have the electron on a spring picture for this. And we use the Hooke's law, F is equal to minus kx, for our discussion. So here we see the oxygen molecule. So there are two electrons here, and because of the two electrons, there is a sort of a cloud around the nucleus, which is here. So the two nuclei are together. They are sitting together. Sorry, the two nuclei are here, and the electrons are moving in this orbital here, and the centers of the two, the positive charges, this nucleus and this nucleus, the center of the charges comes here, and the distributed electron cloud, the center of the negative charge also comes there. So the centers of the charges are sitting together. So therefore, this oxygen molecule normally does not have any dipole moment. However, imagine the situation that you apply an electric field onto the oxygen molecule. Let us say this is a DC electric field for the time being. When you do that, because of the attraction of the electrons to the positive part of the electric field, the centers will shift because the electrons will move a little bit towards one side, and the nuclei, both nuclei, will move a little bit towards the other side. So when that happens, the charge centers will separate. So you have positive here, you have a negative here. This is an electric dipole. So this is an induced electric dipole, and we can write the dipole moment, mu is equal to minus Ex, and if you take the total number of molecules per unit volume, so you have each molecule is a small electric dipole now, so you multiply the dipole moment of each electron to with the number of molecules per per unit volume, that's the number density. That gives you the net polarization, net electric polarization. So this expression is also written in the form P is equal to epsilon naught chi1e, where chi1 is the first order susceptibility material. Now this is simplified case because when you apply a field in this direction, you also have the induced dipole in the same direction. But in general, this is not always true. Sometimes in many materials, it can so happen that a field that you apply in one direction will give you a dipole moment in a slightly different direction. So this is not impossible. And in such situations, you have to write the equation appropriately. So therefore, in such situations, we use the polarizability tensor. Mu I is equal to alpha ij ej. That way we write, where alpha ij is the molecular polarizability tensor. Now we need free molecules, or at least they're all bound all the time, but they need to be free also. So just to see an example of conjugated molecules and polymers. So let's say conjugated, what happens is there's a single bond and a double bond that alternates in your molecule. So taking the case of the simplest molecule, one of the small molecules, the acetylene molecule, if we map the different electrons in that molecule, this is the way it looks. So we have the K shell electrons, which are closely bound to the nuclei. So these are all nuclei like this, 2, 3, 4, 5, 6. So the K electrons are very close to the nuclei and they cannot be moved around. Whatever force you apply from outside, usually these electrons are not affected at all. So we leave them. Then you have sigma electrons, which are there, but they are a little more extended, but they are also not really very movable by the application of external fields. But then you have pi electrons. These pi electrons, their orbitals extend quite a bit from the chain, from this nuclear chain here, and because of this larger distance of these electrons from the nuclei, if you apply an electric field from outside, then it is possible for that field to make these electrons oscillate accordingly, depending on the strength of the field. So these pi electrons actually contribute to nonlinear optics, because we will see that it's the oscillation of the electron. If it is nonlinear, then that leads to nonlinear optical phenomena. So this is the electron potential well picture for the same situation. You can see the K shell electrons here, the one as state actually, and very down here, very close to the nuclei, and they're a bit down in the potential well. So therefore, we cannot read, they don't really get perturbed that easily. And the sigma shell electrons here, and then pi shell electron states, which are really, really close to the, at the topmost of the potential well. Now we look at the Lorentz atom model. So same thing, the classical electron on a spring picture. So this, if this is a weight on a spring, then as we know, you can make this oscillate. In the same way, an electron here can oscillate because of the applied electric field. Then we can write an expression for the force as a function of distance, F is equal to minus kx. This is the well-known Hooke's law, which is applicable for the electron as well. And we can write it as minus m omega 0 square x. And now if we consider a nonlinear restoring force, then we have to write it like F is equal to minus m omega 0 square x minus ma x square minus mb x cube. And if this corresponds to this kind of polarization, then this corresponds to this kind of polarization. So here you can see the E1 term, E square term, E cube term, like that. Now, once we write a force field in this form, you can write the corresponding potential, and the potential is given by integral f dot dr. So that will give you 1/2 m omega 0 square x square plus 1 by 3 ma x cube plus 1 by 4 mb x to the power 4. So here, as we can see, the first term is this term, is the linear term. The linear term of the polarization, that corresponds to an x square function. So, and the second order nonlinearity corresponds to an x cube term, and the third order nonlinearity corresponds to an x to the power 4 term in the potential. So if you plot this potential as a function of position, then you can see that the parabolic potential is given by the first term, half m omega 0 square x square. So you have to think about it as a simple harmonic oscillator, and we know the simple harmonic oscillator has a parabolic potential. So that is what we see here. It is symmetric with respect to the central point or the zero position. However, look at the next term, 1 by 3 ma x cube. So as I told you, this is what corresponds to x square in the first term, and so therefore this is the second order nonlinearity term. The second order nonlinearity, the square term, actually gives you a potential which is not symmetric because of the x cube term here. So we will see that in the next slide a little better. So the parabolic potential is the black one, and non-centrosymmetric potential is a little shifted like this. The reason for this is that x cube is a positive quantity on the positive side, but it's a negative quantity on the negative side. So therefore, on the positive side, if you add these two things together, you will get a certain value. This is a positive term, this is a positive term, so they get added up on the positive side of x. Qi is x in fact. But if you come to the negative side, then this is a negative term. So this gets subtracted from this term. So therefore, the total potential is a little less. So that is how it becomes asymmetric. So we will look at the significance of centrosymmetry here. Suppose that your potential is centrosymmetric for some reason. The normal reason for having a centrosymmetric potential is that the molecule which you consider has a center of symmetry. Like oxygen molecule, it has a center of symmetry. So if it has a center of symmetry, then its potential has to be symmetric, and if you have this term, then the potential cannot be symmetric. So that is very obvious from this expression and from the picture. So for centrosymmetry to exist, if your molecule is centrosymmetric, then you will not have these terms. X to the power 3 term will be 0. Similarly, x to the power 5, x to the power 7, they will all be 0 if your material has center of symmetry. So what that means is that the centrosymmetric materials will show only odd order nonlinearities. There is no second order term. There is no chi2 for them. Chi1 is there, chi3 is there, chi5 will be there like that. But they won't have chi2, chi4 and all that. So for chi2 and chi4, all that to exist, you should not have a centrosymmetry in your material. This is the reason why for generating even order nonlinearities, so what I mean is second order nonlinearity, if you want to generate that in a material, then you have to look for something that does not have a center of symmetry. And the normal easy material to get for this purpose is crystals. So many crystals are anisotropic. They don't look exactly the same in various directions. So therefore, they have no center of symmetry, and those materials can be used for second order nonlinearity applications like second harmonic generation. Now let's also see the potential for the third order susceptibility. So here I have written all the terms in the potential, x square term, x cube term, and x to the power 4 term. So this is what the x square term is parabolic potential for the linear response. And here we have the second order response. You can see the asymmetry here, here and here. And here we have the third order term, and the third order term is x to the power 4 term in the potential. And as we know, x to the power 4 is a symmetric function. It has to look exactly the same in both directions for plus x and minus x. And the difference here compared to this, because this is also symmetric, this is symmetric, this is also symmetric, but then you see that this is exactly parabolic and this is not, because you see a bend here. It looks like a bell, it's symmetric, but it's not exactly parabolic. So that's the situation in the potential for third order materials, and parabolic is what for first order materials, and asymmetric is what for second order materials. And it's not difficult to calculate some approximate values for the second order and third order nonlinear susceptibilities, and these turn out to be 10 to the power minus 8 ESU for chi2 and 10 to the power minus 15 ESU for chi3. And if you look into this textbook, Nonlinear Optics by Voigt, then it is possible to get more idea about these quantities. So we will have a brief look at harmonic generation, its phenomenology. So as we just saw, if you want second harmonic in a system, then that system has to have a lack of center of symmetry. How do we see this graphically? So let us say this is a fundamental wave at a certain wavelength, and this is its second harmonic. So the second harmonic, as we know, has double the frequency. So when the frequency is double, the wavelength is naturally half. So you have a system where you have a fundamental frequency, and a second harmonic also is generated by a nonlinear optical process. So if that is the case, what will be your polarization like? So your polarization will be the sum of both. So you have to sum this with this, and you immediately see that this is the resultant polarization in your system. And obviously this is not symmetric, because here there is more and here there is less. So the combined wave is asymmetric. Now look at third harmonic generation. Here this is the fundamental wave, and this is its third harmonic. And the third harmonic is 3 times the frequency, 3 omega. That's why it looks like that. Now, if you add these two things together, you will get something which is symmetric. So this wave is symmetric. Only thing is, it's not purely a sine wave. Now, we know, how do you find out the frequency components in this? This is something in time. So this is the amplitude variation in time. And if you want to find out the frequency components in this, what you need to do is to take a Fourier transform. So when you do the Fourier transform, you can actually see the higher frequency components like this. And these concepts actually come, we know about negative feedback and all that. So when we do negative feedback, these kind of higher harmonics in the amplifier will die down a lot. So their value will be much less. So if you don't have harmonics in an amplifier, then that's a good amplifier. It's a high fidelity amplifier. But in NLO, that's not what we need. In NLO, we need harmonics. We will do all kinds of tricks to make harmonics. Okay, so what is second harmonic generation? I've been telling you about it, but I did not introduce that. So look at this experiment. So here is a ruby laser. This experiment was done in 1961. So as we know, the ruby laser was the first laser to be made. That happened in 1960. So just 1 year after that, people did this experiment. So there's a ruby laser here. There is a lens that focuses the laser beam, and then there's a quartz crystal. And here there's a prism and emitting lenses. So now let's try to solve the wave equation for linear induced polarization. So for low irradiances, that is when the input light is not very strong, the polarization is proportional to the incident field. So our linear equation P is equal to epsilon naught I1E. And in the simple case, the wave equation becomes you just need to rewrite P like this. And then LHS remains the same. In the RHS, you can write 1 over C naught square chi d square E by dt square. So this can be rewritten in this form. D square E by dz square minus 1 plus chi by C naught square d square E by dt square is equal to 0. So when you write an equation of this kind, you can get a solution for that equation in this form. E is a t is proportional to E0t cos omega t minus kz. So we know this is a cos function. The cos function will oscillate. So this is the oscillating wave with the plane wave, oscillating plane wave, which is a solution for this wave equation. And here omega is given by ck, and c, so velocity of light, is c naught by n, where n is the refractive index of the medium through which your light is passing. And the refractive index n is given by 1 plus chi to the power half. So this chi is the linear susceptibility. So thus the refractive index depends on the induced polarization, which in turn depends on the susceptibility, linear susceptibility chi. Now what is the effect of a nonlinear medium? So if you have a nonlinear medium, and of course every medium is nonlinear. There is nothing like, there is no distinction like a linear medium and a nonlinear medium. All media are nonlinear. But the nonlinearity is in various degrees. And if you get media which are highly nonlinear, then it's easy to measure the nonlinearity in them. So that's what we always look for, materials with more nonlinearity compared to the other materials. So the nonlinear polarization reads like this. Epsilon naught into chi1e plus chi2e square plus chi3e cube, it goes, it's a Taylor expansion. And so what's the effect of the nonlinear terms? So you have to put this P into the wave equation. And when you do that, so when you substitute for P like that, then you will see that your equation is going to change. So the second order term here, take the case of E square. So if you want to calculate what is E square, you have to do that in the wave equation to solve it. So when I am trying to do that, let me see what is ET. So ET is proportional to e to the power I omega t plus E star e to the power minus I omega t, because you take this as a complex quantity. Now what is ET square? So ET square is going to be proportional to E square e to the power 2i omega t plus 2 modulus E square plus E star square e to the power minus 2i omega t. Now, the most important thing you have to note here is that we started with an electric field of this kind. So in this expression, what do you see? This E is the amplitude of the electric field, and this is exponential I omega t. So it is like, it's same as writing e to the power I omega t. So when you have an I term in the power of an exponential, immediately you have to know that it's an oscillating term, because e to the power ix is equal to cos x plus I sin x. So you have a cos function, you have a sine function, they are oscillating functions. So this is an oscillation, what you see here. Now if it is an oscillation, it has a frequency, and that frequency is given by the argument in this. So here we started with omega, but we ended with 2 omega. So that's the most important observation you have from this expression. Now this 2 omega is double the frequency of the original beam, and that is what we call second harmonic. In fact, second harmonic is just one of the many NLO effects that can happen. To see this is in a more generic way, let's consider two different frequencies, omega 1 and omega 2, to interact with each other in a nonlinear medium. So therefore, ET is now proportional to E1 e to the power I omega 1 t plus E1 star e to the power minus I omega 1 t plus E2 omega 2 plus omega 2 you see here, minus omega 2 you see here. So this is what ET is. Now take ET square, calculate ET square like we did earlier. So you have to multiply each of these terms with the same terms, and when you do that, you will see that there is second harmonic generation of both frequencies. So from omega 1 you get 2 omega 1, from omega 2 you get 2 omega 2. So second harmonic is generated for both frequencies. Then there is a sum frequency which is generated, omega 1 plus omega 2. Then omega 1 plus omega 2 again. So that's the same thing. And difference frequency, omega 1 minus omega 2. Here also you have the same thing. And then something called DC rectification. This is nothing but a small electric field which you will see in your material. So this is what happens, and all this is happening in the optical domain because of the electric field in the electromagnetic radiation. So in some generation you add two smaller frequencies to get a higher frequency. That is what's shown here. Two smaller frequencies, omega 1 and omega, your inputs, and your output is one high frequency. In difference generation, you have omega 1 you can consider as omega 3 minus omega 2. So your final output omega 1 is one small frequency. So you see that here, and that is a difference between these two frequencies, omega 3 and omega 2. And in parametric generation, you have one high frequency as your input, omega 3 is your input, and you have two smaller frequencies as your output. Now the advantage in parametric generation is that you can keep your input the same, but you can continuously vary omega 1 and omega 2 in such a way that omega 1 plus omega 2 is always equal to omega 3. So these are the different facets of parametric mixing in nonlinear optics. And parametric down conversion, parametric generation, oscillation, amplification. There are slightly different variations of the same theme, but it's basically the same thing. There are three frequencies here, and they reinforce each other in various ways. So that is the general premise of parametric oscillation. So all that is very nice theory, but it has to work in practice also. So we can buy these kind of lasers from companies. There are a few companies which sell optical parametric oscillators. So as I said, the advantage of the optical parametric oscillator is that you can have just one input. You can change the color. You can tune the frequency. Omega 3, which is the input, is equal to omega 1 plus omega 2. And you can continuously change omega 1 and omega 2. So this is what we mean by a tunable laser, a frequency tunable laser or a wavelength tunable laser. You can continuously change the color of the laser. And obviously it has many applications. So that much about the generation of new frequencies by nonlinear optics. So now we will look at the generation of laser pulses, means of nonlinear optical techniques. So there are two kinds of methods for this. One is called Q switching and the other is called mode locking. So Q switching is a technique that we use for making nanosecond pulses. So what is done here is that the Q factor of the laser cavity is modulated. Now what is Q factor? Q factor is the gain in a laser cavity. We know that shown, it is somewhere here, but a polarizer is shown, and then something called a Pockels cell also is shown. So this Pockels cell is an electro-optic modulator. So what happens? So that is where the NLO is coming in. Electro-optic modulation is a second order nonlinearity. The generation of birefringence by electro-optic modulation. So what is done here is the Pockels cell is a crystal. It's basically a crystal, and the way it works is when you apply a high voltage to the crystal, to the Pockels cell, it becomes birefringent. the nature of birefringent series, it becomes a lambda by 4 plate. Now, what is a lambda by 4 plate? There are lambda by 4 plates, lambda by 2 plates, and all that. So a lambda by 4 plate is something which makes a linearly polarized beam circularly polarized. So this polarizer in the laser cavity makes the laser beam linearly polarized, but when it passes through the focal cell, it becomes circularly polarized. Now there is the other mirror here, and it gets reflected at the other mirror, and when it comes back, the circular polarization becomes linear polarization again. Or in other words, if you started off with a vertically polarized beam like this, after 2 trips through the focal cell, it becomes horizontally polarized. So if the returning beam is horizontally polarized, then it will not pass through the polarizer, because this polarizer allows only vertically polarized light. So what happens? It stops. Or there is no round trip in the laser cavity. So you might know that for stimulated emission to build up in a laser cavity, it requires several round trips, multiple round trips like this. But that is getting stopped because of the shift in the planar polarization. So what you do is you excite your laser medium by a flash lamp or something, and the population inversion builds up. It keeps on building up like this, but you keep the focal cell also switched on. Because the focal cell is switched on, it doesn't allow the laser action to take place. So because laser action does not take place, the population inversion keeps growing. However, at one particular point where the population inversion is almost saturated, because you know there is no point in pumping any further. At that point, you switch off your focal cell. So the focal cell is switched off, and the moment the focal cell is switched off, it is just like a piece of glass, because it's a crystal, and if no voltage is applied to it, then it's sitting there just like a crystal, a piece of glass. So there is no flip in the polarization. The beam passes through, and it makes multiple trips like this, and amplification takes place, and finally, and then you have the laser beam. The advantage here is that you don't allow laser action to take place until the population inversion reaches a maximum. So if you do that, the output pulse that you get will be very energetic. So you get a very short pulse, and it contains a lot of energy also. So this is what we call Q switching. And even if your flash lamp, because I told you very probably it's a flash lamp sitting here exciting your laser medium, it can have microseconds lifetime, but the laser pulse that you get at the output will have only nanoseconds duration. So this is the advantage of Q switching, and Q switching is an application of NLO because we use the focal cell here. There are other methods. Without NLO also you can do Q switching, but nowadays almost everybody is doing the focal cell modulation for getting Q switching. Now there is another method called mode locking. If you want to make picosecond and femtosecond pulses, Q switching is for nanosecond pulses. So what is done here is to synchronize the phases of all the cavity modes to get very short, intense pulses. So as we know, the laser cavity is a cavity. It's like a mechanical cavity in some sense. A mechanical cavity, a resonance column experiment in the college, we do resonance column experiment. So that is a mechanical cavity. You can adjust the length of the pipe so that the column inside, its length also can be changed. Similarly, an optical cavity is bounded by mirrors, 2 mirrors, and you can put various things in the cavity like a laser medium, the pumper for that and all that. However, whenever you have a cavity, there are longitudinal frequency modes in the cavity. The same way in a resonance column, you can have different frequencies resonating to the length of that resonance column. Here also, in the same way, it resonates to the length of the cavity. The cavity length will decide which are the frequencies of the modes inside, and also more basically, which is a separation C by 2L, that is the frequency separation of adjacent frequencies in an optical cavity. So these are those adjacent frequencies. If this is the optical cavity, you can see this is one wave, this is another wave, this is another, this is another. So 5 different waves are shown here, and each of them has a different frequency. And those frequencies are separated by C by 2L. Now, if you can lock them in some way, so what it means is, by doing something, you bring all the phases the same at one point in time. If you can do that, then you will get a very sharp pulse. So that's what you see here. So if you look in the time domain, at this point where there is a constructive interference between all the longitudinal modes, you get a sharp pulse. So if you look at the envelope of this, it's this envelope which is drawn here. So that one gives you a sharp pulse, and this will happen continuously. So these pulses will come one after the other, and these are very short laser pulses. So typically what happens in a normal mode locked laser is that the pulse duration possible is given by this quantity. I'm not really going into all those details. So except to say that if you take a helium neon laser and if you mode lock it, then you can get something like 200 picoseconds, the minimum pulse width. So this pulse width will be something like 200 picoseconds. You know that it's a very, very short pulse. However, we can go even lower. Like if you have a titanium sapphire laser, then you can have an even shorter temporal width of 3.4 femtoseconds. So this is actually the record at the moment. Nobody has been able to break this record in a mode locked laser. And there are some ways of going less than this, but it is not by NLO. You have to adopt some other techniques, and they are very elaborate and like high harmonic generation. So you have to generate very high harmonics, and then and they together they'll give you attosecond laser pulse. But this is mostly laboratory curiosity. It hasn't really come out into the public as a commercial offering. So here you see an example of mode-locked ultra-fast laser pulses seen on an oscilloscope. So one after the other. This particular pulse train has a frequency of 82 megahertz. So what it means is every second 82 into 10 to the power 6, that many laser pulses are coming out from your laser. So we just saw the application of nonlinear optics in the making of nanosecond, picosecond, and femtosecond pulses. So now we will see another aspect of nonlinear optics, nonlinear refractive index and nonlinear absorption. So an example of nonlinear refractive index is self-focusing of a laser. So that is, the net refractive index of a medium can be written in the form N0 plus N2I. So this N0 is the normal refractive index, and what is N2I? N2I is the nonlinear refractive index coefficient. So in addition to N0, you have this term N2I, which you need to add when the intensity is really high. So as you have already seen, all the nonlinear optical effects are visible when the intensity is high. So that's why from this expression it's obvious. If the intensity is very low, then this term will not have any significance compared to this term. And the effective refractive index is nothing but the normal refractive index, N0. That's a linear refractive index. Now, let's see how this equation come into action. So think about a spatially Gaussian laser beam. So a Gaussian beam is very, very common because that's the lowest order mode in an optical cavity. So if you just allow a laser cavity to lace, in many cases you will see that you get a Gaussian beam. So what is a Gaussian beam? A Gaussian beam is nothing but, especially a Gaussian beam is nothing but if you take a cross section of your laser beam, let's say you keep a piece of paper, white paper, in the laser beam path, and you look into that spot. You look onto the laser spot using a camera or something, then you will see that the central portion of the laser beam is very strong, it's very intense, and the intensity reduces towards the edges. So this is this kind of a shape it has. Now look at this expression, the refractive index of the medium. And imagine this beam is passing through a medium, just glass. The refractive index is given by N0 plus N2I, and N2 is a constant of the medium. And we know I is a maximum at the center. So in this region, in the central region, the total refractive index will be more compared to the edges. So here you have the total refractive index less compared to the total refractive index, which is more here. Now, what is the implication of this? The implication is that when you have more refractive index somewhere, it reduces the speed of light. So the velocity of light is not a constant. We know from the theory of relativity that the velocity of light is an absolute constant and it cannot change in any way. So what is Reji Philip saying that the velocity of light is not so constant? So you have to understand that that statement in the theory of relativity is for vacuum. So the light velocity is a constant in vacuum, in wherever you look in this universe. That is what it means. When light passes through a material, its speed is completely dependent on the refractive index of that material. So we just saw that in this region, the refractive index is high. So the velocity of light in this region will be less because this is given by C over N, where C is the velocity of light in vacuum. Divide that by the refractive index, that is the velocity in a medium. So C by N is smaller here compared to here. So the light will pass faster in this region and slower in this region. The effect of this is a focusing on the light beam. So this is what we call self-focusing, because we did not use a lens. Normally we know if you want to focus a beam, you have a material. The way is to use a laser beam which has a Gaussian shape. There are some laser beams which are not Gaussian. They will be what we call top hat. So they will be just like the same intensity all across the cross section. Those beams will not focus like this. Only a Gaussian beam will focus like this. And this is called self-focusing. It has some applications. For instance, we just saw more. Something called what we use is the self-focusing of a Gaussian laser beam. In glasses, this has been studied a lot because many of these glasses are hosts for optical fibers, and the N2 value, we need to know this for optical fibers because we want to minimize the optical nonlinearity in fibers. So that's why all these classes have been studied, and different materials are given different values for N2, as we see from here. So when there is two photon absorption in a fluorescing medium, it can sometimes give you a fluorescence. And whenever there is fluorescence of this kind, microscopy can be done. So I'll explain this to you. Imagine there is a laser beam here, and there's a focusing lens here, which focuses your laser beam into one particular material, and then from the focal point, it expands like this. So here, this is your one photon absorption fluorescence, and this is your two photon absorption fluorescence. So I have to give you an example here. A very good example is that of the dye rhodamin 6G. So this dye is a laser dye, and it's a very good fluorescing material. So if you excite your dye with 532 nanometers, then the dye will, 532 is green color. 532 nanometer is the second harmonic output of an Nd:YAG laser. So if you use that wavelength, the green wavelength, to excite rhodamin 60 dye, then it will emit in the yellow and red region. So that fluorescence of the dye. So if you do that, I will see my cuvette. This is a cuvette. It's a glass container in which I have taken the dye, let's say. So I will see that the entire cuvette is illuminated. The entire cuvette is illuminated. But imagine, instead of giving 532 nanometers, I am taking the fundamental wavelength out of my Nd:YAG laser, which is originally produced by the Nd:YAG laser. That is 1064 nanometers. So double the wavelength, half the frequency. So this is what I get. It is possible for me to get at the focal point only, not everywhere. At the focal point where you have maximum intensity, an effect called two-photon absorption will take place. It can take place. And two-photon absorption requires very high intensity. Without that, it just won't happen. As we know, for many diseases, including cancer, a lot of imaging needs to be done. So if there are cancerous cells inside the human body, then one way to find it out, even in the case of some CT scans, one way to find out or to see a region exactly is to inject a dye into your bloodstream. So this dye will go, and there are also some labels along with it. So it will go and stick to the affected areas. It won't stick in any other place. And then if you can use a laser beam, then, or some kind of imaging technology, then you don't want an entire area to be illuminated. You want only, if you want to do it optically, whatever method you are taking, in optics also this is correct, you don't want some healthy cells to show light in addition to the unhealthy cells. In any cancer treatment, you will treat only the affected cells. You don't really want to remove the healthy cells from a patient. So something like this will give you more accuracy because it doesn't really lighten up the entire area. So this allows you to pinpoint better onto your target, and therefore it is possible for the doctor to give a better treatment to the patient. So just one application. So these are some applications which are possible with this kind of two-photon absorption and fluorescence and microscopy. And this is how the two-photon induced fluorescence is going to change. So to know whether your fluorescence is from two-photon absorption or one-photon absorption, the only thing you need to look at is how it varies with the incident intensity. If you draw a log-log plot, and if you take the slope, and if the slope is close to 2, it is about 2, then you can be sure that it is two-photon absorption induced fluorescence. If the slope is close to 1, it is a one-photon process. So how do you measure nonlinear refraction and nonlinear absorption? So this is the most popular experimental method at the moment. So this is called the C-scan experiment. So to measure nonlinear absorption, you have to make use of the open aperture C-scan experiment. The open aperture is one flavor of this experiment. I'll tell you what it is in a moment. So you have a laser beam. So this is the sample you want to analyze. So what you are trying to do here is to find out whether this sample has nonlinear absorption in it. And what is nonlinear absorption? When you put more and more light into it, if it absorbs, if it does things like two-photon absorption, excited state absorption and all that. If it does that, it has nonlinear absorption. If it doesn't, then it does not have nonlinear absorption. However, this experiment will give us an answer to this. So the laser beam comes here. So there is a beam splitter. A small part goes to a detector. This is a reference detector. The main part goes through a focusing lens through the sample, and then it goes to a detector. So what happens here is that in this experiment, we will move the sample from one side of the focal point to the other side, like this, from here to here. And as we move, obviously, the intensity falling on the sample keeps changing. And as we just saw, this intensity variation is possible by this experiment, and you can draw the effect of the nonlinear absorption as a function of position. So we can imagine it's not difficult to see that at the focal point, you have maximum intensity in the system, and that is where you can expect maximum nonlinearity from your material. And as you go away from the focus, the intensity decreases because this is not a focal point. I mean, the beam is bigger, and then progressively the nonlinearity will decrease. Now you can draw a graph with Z on the x-axis and your transmission on the y-axis. That is called an open aperture C-scan graph. And from that graph, it is possible for you to find out the nonlinear absorption coefficient. Now the other part is the nonlinear refractive part. For that, we make use of a closed aperture C-scan experiment. And here, we put an aperture in the beam. So it is this aperture that allows us to measure the closed aperture part. I mean, this is a misnomer. They should have given some other name. By the way, Srikanth has been, both of us, Srikanth and I, both of us worked at the University of Central Florida, where this technique was invented. So I'll come to this in a moment. So somehow they named it closed aperture. So whereas it is not fully closed, it's actually partially open like this. So if you have something like this, then you can find out the nonlinear refraction of your material. The only constraint here is that it needs a spatially Gaussian laser beam for the self-focusing effect to occur, and an aperture is required to measure the self-focusing effect. So this very popular technique, the C-scan, was discovered by Mansoor Sheikh Bahaye and professor under the guidance of Professor Vance Fryland in this department called Creole in the University of Central Florida in Orlando, in the US. So I had worked in the university for a year in 2012, and a little later Dr. Srikanth also worked in the same department, but not in Creole, but we happen to know the people there. And in fact, I told you that I had met Bloombergen, and that was in fact in this department where conference was happening in 2012. And this is how an open aperture C-scan curve will look. You can see this is the focal point, and the normalized transmittance of your sample is a minimum there. And away from the focal point, it is linear, it's normal. So from this curve, so what you see here, these are the experimental data points. This is an actual measurement in my lab. And here you can see the numerical fit. There's an equation which governs this process, and you can do that fit here, and from that fit, it is possible for us to find out the nonlinear absorption coefficient. Now there is another experiment which is used for finding out chi3. Of course, C-scan is good enough to find out chi3 of your material. Only thing is you have to do two different experiments. The open aperture part will give you the absorptive part of chi3, which is actually the imaginary part of this complex number, and the closed aperture part will give you the real part of your chi3. So you need both the real part and the imaginary part to find out chi3. Now there is another experiment called four-wave mixing. In fact, historically, four-wave mixing came before C-scan. In four-wave mixing, you can get chi3 in one single experiment. But the thing is, you need three laser beams there. You can use the same laser, in which case we call this degenerate four-wave mixing. And one laser beam is split into two parts like this, three parts in fact. So one goes like this and comes back like this. The second beam goes like this and goes like that. And at the sample, we will have 3 beams. And like this, forward pump, backward pump, and probe. So 2 pumps and 1 probe. If you put your nonlinear medium in this fashion and set it up an experiment like this, then you will get the forward mixing signal back from the sample in the same direction as that of the probe. So this is called a phase conjugate beam. And you have to separate the phase conjugate beam out of it. From that, we can find out the value of chi3. And this experiment can be set up in another geometry also, which is called the boxcars geometry. The previous geometry is called the phase conjugate geometry, and this geometry is called the boxcars geometry. It can be done in either way, and this is the result. So you increase the input intensity of your laser beams, and then the signal intensity also increases like this. So you use the equation, and you get a fit on that, and from that fit you find out the value of length. Okay, so now we come to laser spectroscopy applications of nonlinear optics. So there are many techniques which became prevalent after the arrival of lasers. One of these is frequency comp spectroscopy. This is for precise atomic spectroscopy, frequency comp spectroscopy. Then there is photoacoustic spectroscopy. So what you do here in photoacoustics is to generate acoustic signals by means of laser beams, and then these acoustic signals are measured by using transducers. So you can use very, very small microphones if you are working with gases, and if you are working with solids and liquids, then you can have piezoelectric microphones which are more effective for that. So from the acoustic information that you get a lot of information about the material. Actually, photoacoustic spectroscopy nowadays is again used in medical imaging more than anywhere else. Then we have Raman spectroscopy. And Raman spectroscopy, in the morning, there was an excellent lecture by Professor Vijayan, and he has clearly, I was seeing it, and he has clearly told you about the theory behind Raman spectroscopy. The polarizability of the molecule has to change. Then only you see the Raman lines. So he told you clearly about the distinction between normal infrared spectroscopy and Raman spectroscopy. So these two are mutually complementary techniques. So if you want to know a molecule perfectly, then you have to do both. You have to do IR spectroscopy as well as Raman spectroscopy. Again, Raman has, in addition to many other applications, Raman has medical applications as well. Then we have laser-induced fluorescence. This is many materials, particularly emitting materials, phosphors and all that kind of light-emitting diodes. So all those things are studied by means of fluorescence. Then there is something which is important called laser-induced breakdown spectroscopy. This is essentially high-order NLO. This is what I showed you in the beginning. We have the perturbative NLO, which we are generally talking about in this talk, and then we also have the intense field NLO. So this comes in the intense field NLO regime, laser-induced breakdown spectroscopy. So what is done here is you send a very powerful laser beam onto your target, which can be a little away, in fact. So what you want to do here is to find out the elements present in that target. So you send a laser beam, a plasma is formed at the target because of the very high intensity, and you observe that plasma. You measure the plasma spectroscopically using a spectrometer. So that plasma will give you information about the contents in that material. Now there are a few specific areas where this technique is very useful. One is space investigation. Like, these rovers which go to the surface of the Mars and all that. So those instruments actually have ellipse spectrometers inside. So the rover can go to a convenient place and aim the laser beam onto a rock or something shoot a few pulses and measure the fluorescence, the plasma emission that comes out of the target. And from that information, it can find out which are the elements present there. In earlier days, before LIPS and all became popular, if you go to moon or something, then astronauts actually used to bring material back from there. So moon, rock, etc., they're here. They have brought back these things. And then these were analyzed in our labs, in the American labs and Russian labs, basically. Nowadays, for one thing, man can go up to moon and all, but going beyond that is not an easy task. So, but you want to investigate anyway. So in such situations, LIPS spectroscopy is very useful. There's no need for humans to go. Instruments can go, rovers can go, and they can make the measurement there itself and relay back the information to us. So LIPS are such applications. And then there is another very important area called ultra-fast time-resolved spectroscopy. So here, what happens is we use very short laser pulses, like femtosecond and picosecond laser pulses to do spectroscopy. And this is usually called pump probe spectroscopy. So in pump probe spectroscopy, we look at the things which happen in molecules. Like, if you want to find out the excited state lifetime of a material which does not fluoresce. So if it's a fluorescing material, there are ways to find out. You can look at the emission and see what's its lifetime. But if it doesn't fluoresce, what do you do? So then you have to look at other methods, and pump probe spectroscopy is something like that. You can use 2 ultra-fast pulses, and one of those pulses will excite your material and the other pulse will interrogate the excited medium. It will find out by how much time the excitation gets de-excited. So that will give you lifetime information about the upper state. So in this way, people have measured even femtosecond kind of lifetimes have been measured. So all these kind of spectroscopic techniques are very useful, and there are many of them which border on nonlinear optical methods. So the 5th application I will mention is laser machining. There are a lot of things here. What happens is, again, a plasma is generated by multi-photon ionization. The plasma continues to absorb more light and sustains itself until the raised pulse is over. And this is when ablation happens. The ablation of thin films is used extensively in the semiconductor industry for removing conducting ITO electrons on solar cell edges, for trimming resistors, for removing short circuits, etc. in the semiconductor industry. And the industry uses laser machining for die cutting, marking, as well as PCB making and making LED chips, marking LED chips. And you can have a thin film formed on a nearby substrate, not really making it on the target itself. And there are various applications like creating the films of nanomaterials, superconducting materials, thin dielectrics. So all these materials in thin film technology, we have a lot of application for photoablation. So that is one part of machining. And laser micro machining has medical applications as well. So medical device manufacturing, for example, see implants and surgical tools, they require advanced manufacturing processes because small changes in the surface texture, dimensions, and shape can affect their performance. So these have to be pretty, made to the very rigorous standards, and we cannot allow too much latitude in their quality. So therefore, people have found that ultra-fast lasers can process virtually any material without heat dissipation. So when there is no heat dissipation, the accuracy and quality of what you make will be very good. So by this technique, a new generation of coronary stents, finely processed catheters, and surface structured bioimplants have all reached the market through laser micro machining. So this is a photograph of one of those stents, biomedical stents, which I took from the internet. Then another example of laser treatment in laser plasma treatment is KSHEC, which is laser-assisted in situ keratomileusis. So this is originally keratomileusis is a predecessor to LASIK. This involved removing a section of the cornea, shaping it, and then putting it back. So this process was done using a knife, which is called microkeratom. However, now this is much easier, because in LASIK you use a laser and a flap is cut in the cornea, and an excimer laser is used to reshape the exposed stroma. So stroma is the middle layer of the cornea. So this is an example of keratomileusis now, which is done by means of laser beams. It's fast, quite fast and quite safe. And laser surgery can correct these kind of problems: myopia, hyperopia, astigmatism, and all that. Cataract. So all those issues can be handled by lasers. Then coming to communication, optical communication. So that's the last part of my talk. There is an impact of nonlinear optics in optical communication also. So for example, in fiber optic telecommunications, NLO was found to be the fundamental limit to the amount of data that can be transmitted on a single optical fiber. So why this is important is because we have transoceanic fibers. For example, there's a transatlantic optical fiber that goes from New York to Paris. So the cable is laid in the ocean, basically. And it's a very long cable, not a single cable, of course. I mean, there are repeaters, everything is there, but it's a very long distance. So there will be limiting factors which will constrain your freedom to send data through these fibers. So NLO is one of those limiting factors. And as the laser power levels increase, because as we know, this is optical communication which needs lasers. So as the power level of the laser beam increases, the nonlinear optical phenomena will limit the data rates, transmission lengths, and the number of wavelengths that can be simultaneously transmitted. You want to send more number of wavelengths at the same time, because that's when your capacity goes up. So the upper limit on the optical power that can be usefully launched into an optical fiber is due to stimulated Brillouin scattering. Stimulated Brillouin scattering gives you an output which is almost like the input frequency. The shift in wavelength is very less. And the bad thing is the threshold for SBS to happen in a fiber is fairly low. Stimulated Raman scattering can also happen, but the threshold for that is about 1,000 times higher. So therefore, SRS is much less detrimental to fiber communication compared to AS. And the SRS threshold is close to in a typical fiber. Therefore, nowadays, whenever people design optical fiber lines and optical fiber links, they always think about the nonlinear optical aspects of this. So, as a curiosity, when I'm discussing fibers, we know that satellites and fibers were competing with each other because there are a lot of communication satellites in the orbit. And instead of sending data through fiber, it is also possible to uplink the data to the satellite and then downlink that so that data can be transmitted over any part of the globe. And a very good example is a satellite TV, which the dish TV, which many of us have at our homes. So the data goes through satellite and comes back to us through satellite. However, companies look at the cost involved. So sending the satellite up there, maintaining it there, then they have a lifetime. So all those things, everything considered together, nowadays fibers are quite economic. So that's why from the satellite communication era, there is some comeback to the fibers. Not everybody, but fiber also is equally competent at the moment. In the earlier days, the problem with fiber was that there was latency. So what is latency? Even though light is extremely fast, because of the electronic constraints, the speed of data was not up to the mark. So now all those problems have been solved, and fiber is a very good competitor to satellite communication. Okay, so I reached the end of my talk, and I think I took a little less than 1.5 hours. So that's it. There are many more things to say, but in limited time, and I didn't want to really bore you beyond 1.5 hours. So I hope I could tell you a few things about the fundamentals of nonlinear optics and its applications. So thank you very much. If you have any questions, you can ask me now.
Hello, sir. Sir, ഒരു ഡൗട്ട് ഉണ്ട്. ഈ നോൺ ലീനിയർ ഫിനോമിന സ്റ്റഡി ചെയ്യാനായിട്ട് നമുക്ക് ക്ലാസിക്കൽ ഒപ്റ്റിക്സ് തന്നെ മതിയാവോ? മതിയാവും.
അതാണ് എളുപ്പം സത്യത്തിൽ. കാരണം നമ്മള് ക്വാണ്ടം മെക്കാനിക്കൽ കൺസിഡറേഷൻസിന് പോകണമെന്നില്ല. അതില്ലാതെ തന്നെ ക്ലാസിക്കലി മാക്സ്വെൽസ് ഇക്വേഷൻസ് ഉപയോഗിച്ചിട്ട് നമുക്ക് ഒരുവിധം നോൺ ലീനിയർ ഓപ്റ്റിക്സിലുള്ള എല്ലാ ഫിനോമിനയും നമുക്ക് ഡിസ്ക്രൈബ് ചെയ്യാൻ പറ്റും.
ഓക്കെ സർ.
Yeah, this is Indulekha. Could you please expand a bit on comb spectroscopy, optical combs?
What?
Optical combs.
Frequency comb. Okay. So what happens there is, see, I told you about mode locking. So maybe I have to go back a bit. And yeah. Yes. So here, what we do is, actually those slides are not in this talk because I was not concentrating on the frequency part of that. So I can tell you what happens. See, when we do mode locking in a cavity, when we do this, what we get is a very short pulse, very short pulse. So if you take the frequency domain, if you look at the frequency domain of this, so basically what you do is you take the Fourier transform of your very short pulse. You see that it is pretty broad. So for example, in our lab we have femtosecond laser pulses. We have femtosecond system. So it emits at 800 nanometers. It's a titanium sapphire laser, and the pulse width is about 100 femtoseconds. And then if you measure its spectrum, you can see that it's about 13 nanometers in width. And in that 13 nanometers, there are lots of frequencies. So these frequencies are very adjacent to each other. They are very close to each other. Actually, the frequency separation and the pulse repetition rate are the same. Both are given by C/2L. So this frequency separation is only 82 megahertz in our case. So what you have is several emission lines which are very close to each other, which are separated only by 82 megahertz. Now in frequency comb spectroscopy, they do, I don't know much detail about it, but what they do is they use electronic techniques also. And if you want to precisely look at atomic transitions, like atomic absorptions in a collection of atoms, Then
that involved you had a pulse, and then to avoid dispersion, you did something to it. Then you brought it back, and what is going on actually?
CPA, that's what you are talking about. Chirped pulse amplification.
Correct.
Yeah. So I forget her name. This lady got Nobel Prize for that work, and that was a PhD thesis actually. So what happens there is, see, this is what is happening. You have a femtosecond laser pulse, and these pulses are extremely intense because they can destroy materials, because they are extremely short and all the energy is packed in that very, very short time. That's why they are very intense. So how to amplify femtosecond pulses was a problem. That was a technical issue in those days. Because a Mortlock laser like this, it can produce femtosecond pulses, certainly can make, but the energy is very less in that for these lasers. They are called seed lasers because of this. So they used to make only nanojoule kind of energy. But for many applications, nanojoule energy was not sufficient. So people thought of amplifying the nanojoule pulses to millijoules, like that, hundreds of millijoules actually, which would meet many, many requirements. But then the first stage was okay, from nanojoule to microjoule was okay. But the second stage of amplifying from microjoules to was very tricky, because the microjoule pulse itself is very, so the very components which they wanted to use for amplifying these pulses were getting damaged by the pulses themselves. So some solution had to be found. So that's where they discovered CPA. What is done there is to, first you make the femtosecond pulse, then you expand that pulse in time. So for example, 100 femtosecond pulse can be expanded to something like 300 picoseconds in time. When you do that, the energy doesn't vary, energy content is the same, but the intensity actually decreases. So it is like a very sharp pulse like this is spread like this in time. So when it is spread like this, the energy is actually the area under the curve. So the area under the curve remains the same, whether it is like this or this. So from this, you go to this, then you amplify it. No problem, because now the intensity is less. Intensity is given by the amplitude of the peak. It is less, so it does not damage the optical components. So you do the amplification, amplify to your requirement, and in one final step, you compress it back to the original pulse width. And that one particular step, you use a compressor grating for this. So by doing it, you can bring it back to the original pulse shape. But then we always lose the compressor gratings because you have to pay a price for doing this. But all the other equipment, all the other optical components in your laser will be intact. Nothing will happen to them. But this component, compressor grating, will get damaged for a while, and they are very expensive also. Like, I mean, we had to change one of our compressor gratings like this, and that will cost something like 8 lakhs. It's only a small piece of holographic grating, but this is what the company will charge us. So, yeah, that is the principle of CPA, chipped pulse amplification.
Thank you.
Welcome. Yeah, please. It is a third order nonlinear material. All conjugated media, because any material can show third order nonlinearity, because there are no symmetry constraints here. It is only for second order nonlinearity that you have symmetry constraints. I mean, you need to have something which is not centrosymmetric. But many of these organic molecules and all, I don't know whether you are referring to one particular organic molecule which does not show no. Is it like that? Or were you asking a general question?
Good evening, sir.
Good evening.
Sir, I had asked about polyaniline in specific. I know I understand that most materials show this third order nonlinear property. But as to polyaniline, and if you go through literature about organic polymers, it is seen that there is no reference to polyaniline anywhere. Polyacetylene and the like are all considered, but this is not, polyaniline is not being considered. Is there any particular reason for that? That is what I'm trying to ask.
Maybe nobody worked on it. Because I don't see any specific reason for polyaniline not to show third order nonlinearity. Because all materials show third order nonlinearity. So maybe for some reason people did not work on it. I mean, I have had such experiences in the past where I suddenly discovered something which people could do 25 years before. For some reason, nobody did that. Like that. So for instance, we made an optical diode using saturable absorbers and reverse saturable absorbers. These two kind of materials were there for the last 25 years, or I mean, ever since lasers were discovered from 1960 onwards. But nobody ever thought about it. Probably like that, because polyaniline is a good molecule. I don't really see any reason why it should not show third order nonlinearity. Maybe the strength is low or something like that, but otherwise it has to show. That's my opinion about it.
Oh, okay, thank you, sir.
Thank you.
Sir, fluids nonlinear behavior കാണിക്കൂ.
Fluids എന്ന് വെച്ചാൽ ലിക്വിഡ്സ് ആണോ? സാധാരണ ലിക്വിഡ്സ് ആണോ ഉദ്ദേശിച്ചത്?
ലിക്വിഡ്സ് ഗ്യാസസ്
കാണിക്കുമല്ലോ, കാണിക്കും. ഞങ്ങൾ ചെയ്യാറുണ്ട്. ഞങ്ങൾ യൂഷ്വലി ലിക്വിഡ്സിലാണ് കൂടുതലും ചെയ്യുന്നത്, വർക്ക് ചെയ്യുന്നത്. ലിക്വിഡ്സിൽ വർക്ക് ചെയ്യാൻ എളുപ്പം. സൊല്യൂഷൻസ്, ഡിസ്പെർഷൻസ്, ഇതിലൊക്കെ വർക്ക് ചെയ്യാൻ എളുപ്പമാണ്. അതുകൊണ്ട് അതിൽ ചെയ്യാറുണ്ട്. Thank you.
എവിടെയാണ്
Sorry?
നാനോ സെക്കൻഡ് എവിടെ?
ഓക്കെ. ഫെംറ്റോ സെക്കൻഡ് പൾസുകൾ നമ്മൾ ഉപയോഗിക്കുന്നത് രണ്ട് കാര്യങ്ങൾക്കാണ്. അതായത് ഒന്ന്, നല്ല ഇന്റൻസിറ്റി ഉണ്ടാവുക, ഇന്റൻസിറ്റി വളരെ കൂടുക. ഇന്റൻസിറ്റി എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ വാട്ട്സ് പെർ മീറ്റർ സ്ക്വയർ അല്ലെ വാട്ട്സ് പെർ സെന്റിമീറ്റർ സ്ക്വയർ നമ്മൾ ഉപയോഗിക്കാറുണ്ട്. ഒരു മിക്സിംഗ് അപ്പ് ഓഫ് യൂണിറ്റ്സ് ആണെങ്കിലും അത് ലേസർ ഇതിൽ ഉള്ളതാണ്. വാട്ട്സ് പെർ സെന്റിമീറ്റർ സ്ക്വയർ എന്നാണ് കൂടുതലും. അപ്പോ ആ ഒരു ക്വാണ്ടിറ്റി ഏറ്റവും കൂടുതൽ കിട്ടാൻ ഫെംറ്റോ സെക്കൻഡ് പൾസുകൾ വളരെ നല്ലതാണ്. അപ്പോൾ അങ്ങനെ നമുക്ക് ഇന്റൻസിറ്റി ഏറ്റവും കൂടുതലുള്ള എക്സ്പെരിമെന്റ്സ് അല്ലെങ്കിൽ ആപ്ലിക്കേഷൻസ് വരുന്നിടത്തൊക്കെ ഫെംറ്റോ സെക്കൻഡ് പൾസസ് ഉപയോഗിക്കും. പിന്നെ സ്ട്രക്ചറിങ്ങിൽ ഫെംറ്റോ സെക്കൻഡ് പൾസസ് ഏറ്റവും നല്ലതാണ്. കാരണം ഞാൻ മുമ്പേ പറഞ്ഞതുപോലെ ഐ സർജറി ഒക്കെ ഉള്ളിടത്ത് ഈ പൾസുകളാണെങ്കിൽ അത് കട്ട് ചെയ്യുന്നത് വളരെ ക്ലീൻ ആയിരിക്കും. ആ കട്ടെന്ന് പറയുന്നത് വളരെ നീറ്റ് ആൻഡ് ക്ലീൻ കട്ടായിരിക്കും. അപ്പൊ വളരെ കൃത്യമായിട്ട് നമുക്ക് ഒരു ഭാഗം നമ്മുടെ കണ്ണിന്റെ ഒക്കെ എടുത്ത് മാറ്റണമെങ്കിൽ, ഇപ്പോ കാറ്ററാക്ട് എന്നൊക്കെ പറഞ്ഞ ഒരു ലെയറൊക്കെ എച്ച് ചെയ്ത് മാറ്റേണ്ടി വരും. അങ്ങനെ അത് മാറ്റുമ്പോൾ വളരെ ക്ലീൻ ആയിട്ട് കിട്ടാനായിട്ട് ഈ ഫെംറ്റോ സെക്കൻഡ് പൾസുകൾ നല്ലതാണ്. അതിനൊക്കെ നാനോ സെക്കൻഡ് പൾസസ് ഉപയോഗിച്ചാൽ അവരൊക്കെ, കാരണം നാനോ സെക്കൻഡ് പൾസസ് ഒത്തിരി ഹീറ്റ് ജനറേറ്റ് ചെയ്യും. അപ്പൊ ആ ഹീറ്റ് കൊണ്ട് ആ ഭാഗങ്ങളൊക്കെ കുറച്ച് ഡാമേജ് ഒക്കെ സൈഡിലൊക്കെ വരും. അപ്പൊ അതൊക്കെ ഒഴിവാക്കാം ഫെംറ്റോ സെക്കൻഡ് പൾസുകൾ വെച്ചിട്ട്. അത് ഒരു ആപ്ലിക്കേഷൻ. പിന്നെ രണ്ടാമത്തെ ആപ്ലിക്കേഷൻ എന്ന് പറയുന്നത് പമ്പ് പ്രോബ് സ്പെക്ട്രോസ്കോപ്പി. ഞാനത് സൂചിപ്പിച്ചിരുന്നു. അൾട്രാ ഫാസ്റ്റ് പമ്പ് പ്രോബ് സ്പെക്ട്രോസ്കോപ്പിയിൽ നമ്മൾ കണ്ടുപിടിക്കുന്നത് മെറ്റീരിയൽസിൽ നടക്കുന്ന ടെമ്പറൽ ഫിനോമിന ആണ്. ഇപ്പോ ഉദാഹരണത്തിന് സെമി കണ്ടക്ടേഴ്സ് മെറ്റൽസ് എക്സൈറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ ഈ എക്സൈറ്റേഷൻ ഈ ഇലക്ട്രോൺസിനെ വിൽ ബി ടേക്കൺ ടു ദി കണ്ടക്ഷൻ ബാൻഡ്. അപ്പൊ അവിടുന്ന് ഇലക്ട്രോൺ റിലാക്സേഷൻ ഉണ്ട്, പിന്നെ ഇലക്ട്രോൺ ഫൊണോൺ റിലാക്സേഷൻ ഉണ്ട്, അത് കഴിഞ്ഞ് ഫൊണോൺ റിലാക്സേഷൻ ഉണ്ട്. ഇങ്ങനെ 3 സ്റ്റെപ്പിൽ കൂടിയാണ് ഇത് റിലാക്സ് ചെയ്യുന്നത്. ഇപ്പൊ ഇലക്ട്രോൺ റിലാക്സേഷൻ എന്ന് വെച്ച് കഴിഞ്ഞാൽ ഫെംറ്റോ സെക്കൻഡ്സ് ടൈം മാത്രമേ എടുക്കുള്ളൂ വേണ്ടി. ഇലക്ട്രോൺ ഫൊണോൺ എന്ന് പറയുന്നത് പീക്കോ സെക്കൻഡ്സ് എടുക്കും, ഫൊണോൺ എന്ന് പറയുന്നത് പീക്കോ സെക്കൻഡ്സ് എടുക്കും. അപ്പൊ ഇതിന്റെ ഓർഡർ ഓഫ് മാഗ്നിറ്റ്യൂഡ് എന്ന് വെച്ചാൽ വളരെ ഒരു ലാർജ് സ്കെയിലിലാണ്. ബിക്കോസ് 1 ഫെംറ്റോ സെക്കൻഡ് എന്ന് പറയുന്നത് 10⁻⁻15 സെക്കൻഡ്സ് ആണ്. പക്ഷെ 1 നാനോ സെക്കൻഡ് എന്ന് പറയുമ്പോൾ 10⁻�9 സെക്കൻഡ്സ് ആണ്. അപ്പോൾ 6 ഓർഡേഴ്സ് ഓഫ് മാഗ്നിറ്റ്യൂഡ് വേരിയേഷനിലാണ്, അത്രയും വലിയ ഒരു ലാർജ് റേഞ്ചിലാണ് ഈ ഡിഫറെന്റ് പ്രോസസ്സസ് സംഭവിക്കുന്നത്. നമ്മളെ സംബന്ധിച്ച് എല്ലാം എക്സ്ട്രീംലി ഷോർട്ടാണ്. പക്ഷേ നമ്മൾ അവിടെ പോയി നിന്ന് നോക്കുമ്പോൾ അതൊരു വലിയൊരു റേഞ്ച്. എന്ന് പറഞ്ഞ ഒരു ഈജിപ്ഷ്യൻ സയന്റിസ്റ്റിന് നൊബേൽ പ്രൈസ് കിട്ടി വേ ബാക്ക് ഇൻ ഐ തിങ്ക് 2000. അഹമ്മദ് സിവയിൽ ചെയ്തത് എന്താന്ന് വെച്ചാൽ ഫെംറ്റോ സെക്കൻഡ് ലേസറുകൾ ഉപയോഗിച്ചിട്ട് സിവയിൽ തംബ്രോഗ് സ്പെക്ട്രോസ്കോപ്പി ചെയ്തു, ടൈം ഹോൾ സ്പെക്ട്രോസ്കോപ്പി. അവർക്ക് ഇന്നും പ്രൈസ് കിട്ടിയിട്ടില്ല. 3 വർഷം മുന്നേ CPIക്ക് പ്രൈസ് കിട്ടിയത് ഈ ലേസർ ഉണ്ടാക്കിയ ആൾക്കാരല്ല, ലേസറിനെ മോഡിഫൈ ചെയ്തതാണ്. അപ്പോ അങ്ങനെ ചില കാര്യങ്ങളും ഉണ്ട് ഹിസ്റ്ററിയിൽ. എനിവേ കാര്യങ്ങൾ ചെയ്യാനായിട്ട് sure. I didn't know you are attending. Indulekha, questions ഉണ്ടോ എന്തെങ്കിലും?
Hello. Yeah, it was a very clear talk. So, do you have any questions for now?
Oh, okay. Thank you. Thank you so much. Sure. So, thank you so much for the opportunity, Srikanth. I am so happy to have been here and been able to talk to, I don't know how many people are participating because Google Meet is like a wall. I really cannot see anything. I'm only seeing my screen. I'm not seeing any participant or anything. Maybe because I set it up in the wrong way. But anyway, I hope quite a number of people were able to attend. And I'm really happy for the very active questions. And so thank you so much. Thanks a lot for this opportunity.
Thank you.
Thank you. Hello, can you hear me? ഞാൻ മൈക്കും വീഡിയോ ഓഫ് ചെയ്തതാണ്. Yeah, sure. Yeah, okay. Okay, thank you. Yeah.